9.3 Analysis Model. Non-isolated system. Momentum. The outline of this video is as follows. We will begin by defining a new physical quantity called impulse, which describes the effect of a force acting over a time interval. Then, we will establish the connection between this new quantity and an object's change in momentum through what is known as the impulse momentum theorem. This theorem is a powerful alternative statement of Newton's second law. Following that, we will introduce the concept of the time-averaged force. This is a practical way to analyze complex interactions where forces change rapidly, such as during a collision. We will also discuss the impulse approximation, a method that allows us to simplify our analysis by focusing only on the large forces that act during a very short impact. To bring all these ideas together, we will conclude by working through a detailed example of a vehicle collision, applying the concepts of impulse and momentum to calculate the forces involved. We will now focus on non-isolated systems, which are essential for understanding how momentum changes in practical situations. A system is considered non-isolated if it interacts with its environment through a net external force. According to Newton's second law, this net force, when applied over a time interval, causes the system's total momentum to change. We can visualize this process as a transfer of momentum across the system's boundary, either from the environment to the system or vice versa. For example, think of a baseball as our system. When a bat strikes it, the bat exerts a large external force. This force transfers a significant amount of momentum to the ball, causing its velocity to change dramatically. The key idea here is that a net external force is the mechanism responsible for changing a system's momentum. To find the total change in an object's momentum, we can integrate the net force acting on it over a specific time interval. This process leads us to define a new and useful quantity called impulse. We start with Newton's second law, written as the net force equals the time derivative of momentum, or F net equals dp dt. By rearranging this equation, we see that an infinitesimal change in momentum, dp, is equal to the net force multiplied by the infinitesimal time interval, dt. To find the total change in momentum over a finite period, from an initial time ti to a final time tf, we must sum up all these small changes by performing an integral. This shows that the total change in momentum, delta p, is equal to the integral of the net force with respect to time. We define this integral on the right side of the equation as the impulse, symbolized by the vector I. Therefore, impulse is the integral of the net force over the time interval during which the force acts. We often need to understand the effect of a force that acts over a period of time. For this, we introduce a very useful concept called impulse, which measures the cumulative effect of a net force on an object. Impulse, represented by the vector I, is formally defined as the integral of the net force over a given time interval. A helpful way to visualize this is to imagine a graph of force versus time. The magnitude of the impulse is simply the total area under that curve. Since force is a vector, impulse is also a vector, and its direction is the same as the direction of the net force. For example, the force a bat exerts on a baseball is not constant. The impulse captures the total effect of this varying force during the brief time of contact. Finally, notice that the dimensions of impulse are mass times length over time. These are the exact same dimensions as momentum, which is a critical connection we will explore very soon. In short, impulse is a vector quantity that measures the total effect of a net force acting over an interval of time. This slide presents figure 9.3, which gives us a powerful graphical way to understand impulse for forces that change over time. The top graph shows a net force that varies during the time interval from an initial time t_n to a final time t_f. As we established, The total impulse delivered by this force is equal to the area under the force versus time curve. Calculating this area can be complicated if the force changes in a complex way. To simplify this, we can define a time-averaged net force. This is the constant force that would deliver the exact same impulse over the same time interval. The bottom graph shows this concept. The area of the simple rectangle, calculated as the average force multiplied by the time interval, is defined to be equal to the more complex area under the curve in the top graph. This allows us to analyze the overall effect of a complicated force using a single, constant value. Since forces often change over time, it is useful to define a time-averaged force that simplifies how we calculate impulse. The time-averaged net force is formally defined as the total impulse divided by the time interval. This is expressed as 1 over delta t multiplied by the integral of the net force with respect to time, from an initial time ti to a final time tf. This definition allows us to express the impulse vector, I, as the simple product of the average force vector and the time interval, delta, twi. This gives us a constant force that produces the same change in momentum as the original time-varying force. The calculation becomes even simpler if the net force is constant to begin with. In that case, the average force is just the constant force itself. Therefore, for a constant net force, the impulse is simply the net force vector multiplied by the time interval delta, n et t. We can now combine our definitions of impulse and momentum to form a powerful and useful tool, the impulse-momentum theorem. This theorem is a direct consequence of Newton's second law, but it looks at the effect of a force over a time interval rather than at a single instant. It states that the change in an object's momentum, which we write as the vector delta, p, is exactly equal to the net impulse, vector I, exerted on that object. For example, when a bat strikes a baseball, it exerts a large force for a very short time. This force creates an impulse that causes a massive change in the ball's momentum. This theorem is incredibly important because it is the most general statement of momentum conservation. If the net external impulse on a system is zero, then its change in momentum is also zero. This is simply the principle of conservation of momentum for an isolated system. The key takeaway is that impulse is the measure of the total momentum transferred to or from a system by an external force. Let us formalize our understanding of how momentum changes into what we call the analysis model for a non-isolated system. This model is essential for any situation where an external net force acts on our system over a period of time. The foundation of this model is the impulse-momentum theorem, which states that the change in a system's momentum, delta, p, is equal to the total impulse, I, from those external forces. Think of impulse as the mechanism for transferring momentum into or out of a system. This is analogous to how work and heat transfer energy. However, there are crucial differences between the momentum and energy models. First, momentum is a vector, so its direction is critically important, whereas energy is a scalar. Second, momentum accounting is much simpler. There is only one way to store momentum in an object, as its mass times velocity, and only one way to transfer it, via impulse. The key insight here is that momentum transfer is a simpler, vector-based process described by the impulse-momentum theorem. Let us see how the impulse-momentum theorem is a fundamental principle behind modern vehicle safety. In any collision, a passenger's change in momentum is essentially fixed. They have a certain mass and are moving at the car's initial speed, and the collision brings them to a stop. This means the total change in momentum, delta, p, is a set value. Because impulse is equal to the change in momentum, the impulse needed to stop the passenger is also a fixed quantity. Now recall that impulse is the product of the average force and the time interval. If the total impulse is fixed, we have a critical trade-off. We can have a very large force over a very short time, or a smaller, safer force over a longer time. The goal of safety engineering is to minimize the force on the occupants. To achieve this, designers must maximize the collision time, delta T. This is precisely what safety features like airbags and crumple zones do. They are designed to deform and extend the duration of the impact, spreading the fixed impulse out over a longer period. The key takeaway is that by increasing the time of a collision, we directly decrease the average force experienced by a passenger, which is the difference between walking away and serious injury. Let us apply the impulse momentum theorem to a crucial real-world example: an automobile airbag. Airbags work by manipulating the relationship between force, time, and momentum to make collisions much more survivable. In any crash, a passenger's body has to go from moving at the car's speed to a complete stop. This means there is a fixed, required change in momentum, which we call delta P. This change in momentum is equal to the impulse delivered to the passenger, which is the product of the average force and the time interval of the impact. The primary function of an airbag is to greatly increase this time interval, delta T. Instead of stopping in a few milliseconds by hitting a hard dashboard, the person sinks into the inflating bag, stretching out the time it takes to come to rest. Because the total change in momentum is constant, if we make the time interval much larger, the average force exerted on the person must become proportionally smaller. It is this reduction in the average force that prevents serious injury, demonstrating a life-saving application of physics. Now, let us discuss a very useful tool for analyzing collisions called the impulse approximation. This method allows us to simplify complex situations by focusing on the one force that truly dominates the interaction. In many collisions, one force is enormous but acts for only a very brief time. We call this an impulsive force. During the short interval of the collision, this impulsive force is much larger than any other forces present, such as gravity or air resistance. The impulse approximation is our decision to completely ignore these smaller forces when calculating the change in momentum. We assume the entire impulse on the object comes from only the single, dominant, impulsive force. For example, when a bat strikes a baseball, the contact force is thousands of newtons, but it only lasts for about 1/100th of a second. Compared to the tiny force of gravity on the ball, the bat's force is overwhelming. We can therefore ignore gravity during the impact. A key point is that the initial and final momenta are considered immediately before and immediately after the collision. The impulse approximation simplifies collision problems by letting us calculate the change in momentum using only the main impulsive force. Let us apply our understanding of impulse and momentum to a concrete example involving a car crash. In this problem, a car with a mass of 1,500 kilograms collides with a wall. Note the velocities. The initial velocity is negative 15.0 meters per second in the i-hat direction, and the final velocity is positive 2.60 meters per second in the i-hat direction. This means the car reverses direction. The entire collision lasts for 0.150 seconds. Our goal is to calculate the impulse on the car and the average net force it experiences. We can model this using the impulse approximation, which assumes the force from the wall is so large during the brief collision that we can ignore other forces like air resistance. Therefore, the car is a non-isolated system whose momentum is changed by this large external force. We have all the information needed to find the car's change in momentum. This slide presents figure 9.5, which gives us a powerful real-world example of impulse and energy transformation in a collision. We see a car before and after it collides with a wall. The car's velocity changes significantly, which means it experiences a large change in momentum. This change is caused by the impulse delivered by the wall. However, momentum is not the only thing to consider. Notice the extensive damage to the car. This deformation is a result of work being done on the car's structure. The car's initial kinetic energy was transformed into other forms, such as the energy needed to bend metal, as well as thermal energy and sound. Collisions like this, where kinetic energy is converted into other forms, are known as inelastic collisions. This crash test vividly shows that while the momentum of an object changes due to an impulse, its kinetic energy is often transformed during the process. Let us walk through the solution for this example, applying the principles we just learned. First, we calculate the impulse on the car using the impulse-momentum theorem. Impulse is equal to the change in momentum, which is the mass times the change in velocity. It is very important to get the signs correct here. The car's final velocity is positive 2.60 meters per second away from the wall, while its initial velocity was negative 15.0 meters per second toward the wall. Subtracting the initial from the final gives a total velocity change of 17.6 meters per second. Multiplying by the 1,500 kilogram mass gives a total impulse of 2.64 times 10 to the power of 4 kilogram meters per second. The positive sign confirms the impulse was directed away from the wall. Next, we find the average force by dividing the impulse by the collision time. Dividing our result by 0.150 seconds gives an average force of 1.76 times 10 to the power of 5 newtons. This is a very large force, which makes sense for stopping and reversing a car so quickly. Let us consider an important variation on this problem. What if the car did not rebound from the wall? This helps us understand how the final state of a collision affects the forces involved. Conceptually, we can predict that the net force on the car would be smaller. In the original case, the wall's force had to first stop the car's forward motion and then push it back in the opposite direction. If the car simply comes to a complete stop, the wall only needs to provide the force for that first part, which should require less impulse. We can verify this with the numbers. The only change to our calculation is that the final velocity is now 0. The impulse is the final momentum, which is 0, minus the initial momentum. This gives an impulse of 2.25 times 10 to the power of 4 kilogram meters per second. To find the average force, we divide this impulse by the same time interval of 0.150 seconds. The result is an average force of 1.50 times 10 to the power of 5 newtons. This calculated force is indeed smaller than the 1.76 times 10 to the power of 5 newtons we found for the rebounding car, confirming our conceptual reasoning. Let us summarize the essential connections between force, impulse, and momentum. The central idea is that a net external force, acting on a system over a period of time, produces an impulse. We define this impulse as the integral of the net force with respect to time. This definition leads directly to the impulse-momentum theorem, which states that the impulse delivered to a system is exactly equal to the change in that system's total momentum. This theorem is fundamentally another way of expressing Newton's second law. A key practical insight comes from this relationship. For any given change in momentum, the average force is inversely proportional to the interaction time. This is why you pull your hand back when catching a fastball. Increasing the time it takes to stop the ball reduces the average force on your hand. This framework is what justifies the impulse approximation, allowing us to analyze collisions by focusing only on the large, short-duration forces and ignoring smaller ones like gravity. Let us apply our understanding of impulse and momentum to these two review questions. First, consider the rubber ball and the lump of clay. The key here is to determine which object undergoes a larger change in momentum. Because impulse is equal to the change in momentum, the clay hits the wall and stops, so its momentum changes from its initial value to 0. The rubber ball, however, has to be stopped and sent back in the opposite direction. This reversal requires a significantly larger change in momentum. Therefore, the rubber ball experiences a greater magnitude of impulse from the wall. Second, let us think about the boxing technique. This scenario is a direct application of the relationship between average force, impulse, and time. The total impulse delivered by the punch is essentially fixed. However, we know that the average force is equal to that impulse divided by the time interval of the collision. By riding the punch, a fighter intentionally increases the duration of the impact. For a constant impulse, increasing the time interval directly reduces the average force exerted on their head, making the technique much safer.